Hi, welcome to ASMTower software tutorial videos. We will define the wind load parameters. Open the wind load group. Open the design code data dialog box. The design code is ANSI-TIA222G. Back to drawing. Set the basic wind speed 38.89 meters per second. Set the service wind speed 27.78 meters per second. Set the sway limit equal to 1 degree. Set the twist limit equal to 1 degree. Click OK. The four-sided lattice towers may need a plan bracing to maintain their square shape or to reduce the buckling length of the horizontal members. We'll add a plan bracing at the top of the tower. Open the Geometry group, open the Lattice Panels group, and open the Plan Bracing dialog box. Set the elevation of the bracing equal to 55 meters. You can select the bracing type from the bracing type list. Select the PLX1 type. In element size, you can set multiple profiles to the plan bracing. If you select single profile, all members of the plan bracing will be assigned to the selected profile. Select a 60x4 angle. Click OK. Click Update to refresh the graphics. To zoom in, rotate the mouse scroll. You see the plan bracing is added to the end of the tower. Click Save. Click Analysis. You have the option to perform linear analysis, p-delta analysis, or automatic selection. Also, you can choose to ignore some type of bracing in the finite element model. I chose not to ignore any bracing in the finite element model. Note the effect of self-weight, wind load and snow load on secondary bracing members is taken into the finite element model, whether included or excluded from the model. It is useful to ignore these members in the finite element model when making a preliminary design of the tower. This reduces the time required for analysis and avoids the failure of p-delta analysis due to the buckling of insufficiently sized bracing. Click OK to begin the analysis. The analysis is complete. Click Done. The entire tower is drawn. Some bracing members are red, which means they are not safe. However, since we have not identified any connection to bracing, this design result is calculated conservatively. In TIA222G, the compression strength depends on the effective slenderness ratio KL to R, where K is a non-dimensional factor which accounts for different fixity conditions at the ends and hence may be called the restraint factor. L is the buckling length. R is the radius of gyration. The K factor depends on the restraint condition at the ends for bracing with a slenderness ratio more than 120. Each end should be classified as restrained or unrestrained, depending on the type of connection and the rigidity of the connected member. Single bolt connection is always an unrestrained condition. However, a partially restrained condition is assumed when the connection is made by a multi-bolt or welded connection to a stiffer member. In TIA222G, 3 formulas are available for a bracing has L to R greater than 120. Formulas 4, 5 and 6. Formula 4 is used when the bracing is unrestrained at both ends. Formula 5 is used when the bracing is partially restrained at one end and unrestrained at the other end. Formula 6 is used when the bracing is partially restrained at both ends. The worst case for a member is being unrestrained on both ends, which ASMTower assumes for all members when the user does not specify a connection. This is to ensure conservative tower assignments. To allow ASMTower to automatically calculate the K factor correctly, you shall specify the connection to all bracing. From the Geometry group, Lattice Panels group, Connection group, open the diagonal dialog box. We will define the connection with 2 bolts from 0 to 45 meters and 1 bolt from 45 meters to 55 meters. Set the bottom bolts equal to 0. Set the top elevation equal to 45 meters. Depending on the number of shear planes, users should decide what type of shear connection shall be used. Set it here as a single shear to assume that the bolts are resisting the force with 1 shear's plane. Set the number of bolts equal to 2. The bolt diameter is equal to 12 millimeters. The end distance is the distance between the center of the bolt and the end of the bracing member measured in the direction of the load and is usually equal to or greater than 1.5 times the diameter of the bolt. Set the end distance equal to 22 millimeters. Spacing is the distance between the centers of the bolts measured in the direction of the load and is usually equal to or greater than 3 times the diameter of the bolt. Set the spacing equal to 45 millimeters. In the bolt grade, select A325 from the list. You can add a bolt grade to this list from the bolt database. Select Yes to consider threads in the shear plane. The threads in the bolt make the bolt weaker. The shear strength of the bolts can be evaluated on the basis of their total area without any reduction due to threading when the threads are partially threaded, and you are sure that the threads of the bolt begin after the shear plane. Set Yes to allow ASMTower considering the threads in the shear plane. Set the number of gauges equals to 1. The number of gauges is the total number of bolts that have an end distance on all sides of the member. This will affect the bearing capacity of the bolt connection. Moreover, the number of gauges will be used to calculate the connection length, which is used to calculate the clear buckling length of the bracing and the block shear capacity. Set the block shear net width equals 0 so that ASMTower will neglect the block shear check. The block shear net width is the edge distance of the bolt as shown in this figure. For bearing check, let ASMTower check on the bearing stress in bracing members and in the main leg by selecting None because in our case, the diagonal bracing member is directly connected to the main leg. If there's no gusset plate used in the connection, then we'll set gusset plate thickness equal to 0 and leave the material grade blank. However, you need to define the guessed plate thickness and grade if the diagonal member is connected to the main leg through a gusset plate. Tubular bracing bearing type and tubular leg bearing type are only needed in case of tubular cross-section was assigned to the main leg or bracing members. Single thickness shall be used if only one side of the tubular section resists shear forces, and thus one wall thickness shall be considered in the design. Double thickness shall be used if both sides of the tubular section are resisting the shear forces, and thus double the wall thickness of the cross-section shall be considered in the design. Set it here as a single thickness. By specifying these connection settings for a range of 0 to 45 meters, this connection will be assigned to all diagonal bracing in that range. And those are examples of different types of bracing connections and how to enter them into ASMTower. Click OK. Click Update to refresh the graphics. Repeat the analysis again. Click OK. Click Done. Now you see that most of the bracing members are safe except for 2 panels. This is because after defining the bracing connection, ASMTower found that bracing connects to the main leg with 2 bolts, which can be considered partially restrained at the end with the main leg. Thus, factor K was calculated with a value less than 1. The diagonal bracing members from 0 elevation is painted red, which means it is not safe. Diagonal bracing members that start at 10 meters are not safe and are painted red. The member in the first panel is red, which means it is unsafe. To make it safe, you can increase its size if allowed. Let's continue to define the connections. From the Geometry group, Lattice Panels group, Connection group, open the diagonal dialog box. Select the first row and on the keyboard click the Control button with C button to copy. Select a new row and on the keyboard click the Control button with the V button to paste it. Modify the bottom elevation to be 45 meters. Modify the top elevation to be 55 meters. Modify the number of bolts to be 1. Click OK. Click Update to refresh the graphics. From the Geometry group, Lattice Panels group, Connection group, Main Leg group, open Generic dialog box. Suppose that there are connections in the main leg spaced at 5 meters and the first starts at a distance of 0.5 meters. In other words, a connection to the main leg after each 2 panels. Set the elevation of the leg connections. Set the first elevation equal to 0.5 meters, followed by 5.5 meters, 10.5 meters, 15.5 meters, 20.5 meters, 25.5 meters, 30.5 meters, 35.5 meters, 40.5 meters, 45.5 meters, 50.5 meters. Depending on the number of shear planes, users should decide what type of shear connection shall be used. Let's choose here the double shear connection, to assume that the bolts are resisting the force with 2 shears planes. Try the number of bolts equal to 6. Attention! The number of bolts is the number that will be used in the calculations to transfer the force of the main leg from the side of the upper leg to the side of the lower leg. Here the main leg profile is angled and 6 bolts are used in both sides of the connection. Failure occurs when the bolts fail on only one side. Therefore, the calculation should take into account the only number of bolts that is equal to 6, and in the ASMTower, you must specify the number of bolts equal to 6. However, in the fabrication drawing, the total number of bolts is equal to 12. Bolt diameter is equal to 16 millimeters. The end distance is equal to 25 millimeters. Spacing is equal to 50 millimeters. In the bolt grade, select A325 from the list. Select Yes to consider the threads in the shear plane. Set the number of gauges equals to 2. The number of gauges is the total number of bolts that have an edge distance on all sides of the member. Here are some examples of different types of main leg splices and the number of gauges for each connection. For the rest of the input, we will follow the same concept that we just explained in the diagonal connection. Modify the number of bolts to be 4 for elevation equal to 30.5 meters and more. Attention! The number of bolts is the number that will be used in the calculations to transfer the force of the main leg from the side of the upper leg to the side of the lower leg. Here the main leg profile is angled and 4 bolts are used in both sides of the connection. Failure occurs when the bolts fail on only one side. Therefore, the calculation should take into account the only number of bolts that is equal to 4, and in the ASMTower, you must specify the number of bolts equal to 4. However, in the fabrication drawing, the total number of bolts is equal to 8. Click OK. Let's define the main horizontal connection. From the Geometry group, Lattice Panels group, Connection group, open the main horizontal dialog box. Set the bottom elevation equal to 0. Set the top elevation equal to 55 meters. Set the connection type as a single shear. Set the number of bolts equal to 1. The bolt diameter is equal to 12 millimeters. The end distance is the distance between the center of the bolt and the end of the bracing member measured in the direction of the load and is usually equal to or greater than 1.5 times the diameter of the bolt. Set the end distance equal to 20 millimeters. Spacing is the distance between the centers of the bolts measured in the direction of load and is usually equal to or greater than 3 times the diameter of the bolts. Set the spacing equal to 40 millimeters. As we used a single bolt, the spacing distance does not affect the calculations. If left blank or set equal to 0, ASMTower will assume its default values for the end distance equals 1.5 times the bolt diameter and for the spacing distance between bolts equal to 3 times the bolt diameter. In the bolt grade, select A325 from the list. You can add a bolt grade to this list from the bolt database on the top tab. Select Yes to consider the threads in the shear plane. The threads in the bolt make the bolt weaker. The shear strength of the bolts can be evaluated on the basis of their total area without any reduction due to threading when the threads are partially threaded, and you are sure that the thread of the bolts begins after the level of shearing. In other cases, set Yes to allow ASMTower considers the threads are in the shear plane. And for the horizontal connection, we will follow the same concept that we explained earlier in the diagonal connection. Select the first row and on the keyboard click the Control button with C button to copy. Click OK. From the Geometry group, Lattice Panels group, Connection group, open the secondary horizontal dialog box. Select the first row and on the keyboard click the Control button with the V button to paste it. Click OK. Repeat the analysis again. Click OK. Click Done. This report is automatically generated and stored in the same dictionary where the project file is saved. After ASMTower saves the report, ASMTower automatically opens the report by using the default program that is installed on the computer and is used to open RTF files. This is the cover page for the report. Here you will find the executive summary of the tower analysis. The main diagonal has a maximum usage ratio equal to 1.05, while all other members are safe. The maximum sway in the tower is equal to 0.34 degrees. The main diagonal is unsafe from 0 elevation until the elevation is equal to 2.5 meters. The main diagonal is unsafe from an elevation of 10 meters until the elevation is equal to 12.5 meters. We will offer a strengthening proposal for the main diagonal in these two panels using double back angle instead of the single angle. To do this, from the Geometry group, from the Lattice Panels group, open the Panel Sections dialog box. The first row was used to identify the profiles of the panels from height 0 to height 5 meters. We need to change the size of the main diagonals in only one of these panels. Select the first row and on the keyboard click the Control button with C button to copy. Right-click the first row header and select Insert Row. Right-click the first row header and select Paste. Change the upper height to 2.5 meters. Select another main diagonal profile. The size of the main diagonal bracing is 70 times 5 and the number in the list is equal to 14. There is no double angle back-to-back 70 times 5 angle is defined in the list. Click OK. To add a double angle back-to-back from Geometry group, open the Selected Section dialog box. Select the number 14, which symbolizes the 70 times 5 angle, and on the keyboard click the Control button with the C button to copy. Select a new row and on the keyboard click the Control button with the V button to paste it. In built-up type, select double back instead of single. The angle profile has 2 legs. In the ASMTower database, an angle is defined by defining both the height and width dimensions of the legs. In the built-up section, you can choose the combined leg of the legs. This is necessary if there is an unequal angle, while it does not have any effect for an equal angle because the legs are similar. In built-up side, select height to define that the combined leg in the direction of the height. The gap is the clear distance between the 2 angles. Set it equal to the thickness of the main leg, equal to 12 mm. Click OK. Reopen the panel section dialog box. Modify the main diagonal profile in the first panel. Select the double back-to-back angle 70 times 5. Click OK. Click Update to refresh the graphics. Repeat the analysis again. Click OK. Click Done. You see the colour of the main diagonal is blue, and that means the members are safe. Only one panel height from 10 meters to 12.5 meters is still unsafe. From the Geometry group, Lattice Panels group, open the Panel section dialog box. The 4th row was used to identify profiles for 2 panels from a height of 10 meters to a height of 15 meters. We need to modify the size of the main diagonals in one panel of the 2 panels. Select the 4th row and on the keyboard click the Control button with C button to copy. Right-click the mouse in the 4th row header and select Insert Row. Right-click the mouse in the 4th row header and select Paste. Modify the top elevation to equal 12.5 meters. Select another main diagonal profile. The size of the main diagonal is 65 times 4 angle, and the number in the list is equal to 13. There is no double angle back-to-back 65 times 4 in the list. Click OK. To add a double angle back-to-back from the Geometry group, open the Selected Section dialog. Select the row number 19 of the double angle back-to-back that we just added and copy it. Select a new row and paste to it. From row 13, copy the name of the 65 times 4 angle and paste it into the new back profile row. Click OK. Reopen the Panel section dialog box. Select the double angle 65 times 4. Note that the size of the main leg in this panel is equal to the angle of 120 times 10, so we need to modify the clear gap in the double angle to equal the thickness of the main leg. Click OK. Open the Selected Section dialog box. In the double angle 65 times 5, set the gap equal to 10 mm. Click OK. Click Update to refresh the graphics. To zoom, rotate the mouse scroll. Rotate the view by clicking the +Y button. You see the main diagonal in the lower panel became double angle back-to-back. Let's see the gap distance effect on the double angle in the 3D view. Open the Selected Section dialog box. Set the gap distance equal to a large number, say 120 mm. Click OK. Click Update to refresh the graphics. The distance between the back of the 2 angles is increased. This value was just a test to understand the meaning of gap distance. Set again the gap distance is equal to 12 mm. Click OK. Click Update to refresh the graphics. Click Analyze. Analysis is complete. Click Done. all of the structure is safe.